we are the team that is hosting Android and Chromium. Those are fairly big repositories with their own challenges, and our server implementation is based on JGit, which makes part of my work to contribute also on the library. That being said, the part that I'm familiar with and the part that I'm going to explain here is the server side. We also have people contributing a lot of patches and code on the client side. It's very active, and they have their own features. I don't know all that much about that part, but on the server side, we have enough to talk. Also, just to mention that for questions, you have the www.menti.com, and there you have the code 455805. So for the people online and watching in the streaming, if you have any question, I think that you can post it here, and at the end, we can read those questions and answer them. Thanks. So what I want to follow more or less a chronological order, which is also the steps that we have been building the features. I will explain first, I will introduce server options, then update indices, and those were two enabling features that allow us to implement something called consistency on demand that I will also explain. Then we will move to something more related with performance, that was the reachability checker, and then move to things that are more in the works now, something called sideband all, which we need to do a feature called pack file offloading. And then I will finish with some open items or things that we know that needs to be done in JGit, although they are not exactly in our work plan yet. And then I will pass the baton to Hangwen that will explain the reftables, another big feature coming to JGit. So server options, in May of 2018, we introduced the protocol v2 on Git. The main advantage was that on the fetch part, we could split the things in a command-style fashion. So instead of doing all one thing, tell me what the server has, I decide what to do. Now we can do that in 2 steps and save a bit of the advertisement. And one thing that the protocol v2 introduced was the server options option in those commands, which basically means that if client and server agree on the capability, the client has the ability to send to the server just a blob of data. And that blob of data is unspecified. As long as the server can understand it, it is OK. And this feature, I started working on it because of consistency on demand, but actually it has many other use cases, especially tracing. And I think that that's already working for Gerrit. Because in the case of tracing, you need to give to the server the tracing ID. And actually fits well in this description because that tracing ID is very specific to whatever backend you are using. So how this looks is that when the client does a git fetch, now with the -o, they can put these server options. And on the wire, what happens is that the server announced that it supports ls-refs with server options. So then the client will include a line saying server option equals whatever you put there. In this case, I choose an example with a comma and a key value because really that content is whatever the client decided. And if I recall correctly, in the spec, you can put multiple lines with server option. So this doesn't need to go all together or use a comma as a separator. And from the server side, well, our implementation work was advertising the capability first. Then we did quite a refactor to create these ls-refs and fetch request. That is grouping everything that came into the request. And we made it accessible through a new protocol v2 hook. This hook runs just after parsing the protocol, but before doing any of the calculations and sending an answer back to the client. So yeah, for example, implementing the tracing for the Gerrit side was installing a protocol v2 hook, reading that ID, and setting up the rest of the things in the server. So that was about server options. Then the next thing that we added into JGit was the reference update index. So basically our plan was you have a reference that says that this is master and points to an object ID. You have a reference saying this is master pointing to an object ID, but which one is the most recent version of this? And actually the storage knows it, because if you have the things stored in loose refs inside Git, then at least those refs has a file timestamp. When we use a ref table implementation, the ref table has also some idea of ordering or counting that is called the update index. If you store the things on packed refs, then there is nothing. In packed refs, you have basically a file with refs and object ID. So in that case, you just have the files time of the whole file, and that doesn't really help for this case. Or there are many cases that it wouldn't work. So then what we did is refloat that, update index up to the API, and also adding a flag in the ref database, as you don't know what is the backend that is implementing so what backend is using that repository, we cannot claim that everybody has an update index or decided at compilation time. So then you need to ask the reference database if it supports versioning. If it does, then you can use the get update index on the coming references. And what this gives us is a way to order the references. So now when I get 2 snapshots and I see that the things are different, I can compare what came later. And again, even when it looks pretty simple, just adding a couple of methods in the API, well, this actually meant quite some changes in the code, because every time internally a new reference is instantiated, we need to pass that update index and keep it when we build tags and when we resolve symbolic refs and all the other details. And this was seeming to be a very good idea until we built it with Gerrit, and I discovered that one implicit assumption we did here was always assuming that the references are created by the reference database, which means that we would have control on the update index, but then we discovered that there are references that don't come from the reference database, like, for example, the self-reference in Gerrit. Which means that we end up putting in a lot of places the code of the ref database actually supports versioning, but maybe the reference doesn't have it. So I don't know if this abstraction has been the best of it, but at least it's good enough to implement the consistency on demand. That was our goal. The idea of consistency on demand is basically a problem of read after writing in a multi-master system. So the client does a push to a server. Internally, the server does the duplication to spread that change. But then when the client does a fetch and it goes to a different server, the question is, what is that fetch going to return? If the replication finished, then it will be a consistent view. It will receive what was just pushed. But if the server is still waiting for the replication, then that data is stale. And even worse, the client doesn't know if the data is stale or not. It did a fetch, received the best of the server, and that's it. So this is a problem, especially if you are triggering some build or testing machinery just after pushing, and they are listening to changes, and they want to react to them, and they can react pretty quickly, faster than the replication. So our solution was the consistency on demand, that in this part, so the repository, as a result of the push, or when it announces the push, it will send a token that somehow encodes the state of the relevant state of the server, and it will give it back to the client or the listener. Then the listener can do a fetch and send that token using the server options that we defined before, and the server can decide if it can serve the request based on comparing what comes in the token with the real state of its repository. Then the server can decide what to do, if it can reject the fetch, it can try to replicate, it can decide what to do. That's not really enforced. And this is a feature that we implemented basically in Git, thinking on the Git push, but it has been also relevant in Gerrit and has been some attempts to use it also on the Gerrit part. Then we change a bit gears here towards a topic that came because of performance, that are the reachability checks. So every time you say, I want to fetch a specific commit using just a SHA-1, an object ID, so we can give it back only if it is reachable from a visible branch to the user, and we need to do that reachability check. And this is a very common operation. I mean, the Git tiles API just offers this to fetch objects. But also, how the Git protocol is supposed to work is that you say, hey, I want to fetch, the server tells I have these references with these IDs, and the client asks one of those IDs. And if for some reason the client asks something else, then we need to check. That is really reachable. So reachable from visible branch to the user means that in repositories like Chromium with 1.8 million references, that check can take a considerable amount of time. So the idea here was to use bitmaps as much as possible. Bitmap means once you have the bitmap of a commit, you know anything that is reachable from them. Of course, the caveat here is that not all commits have bitmaps. So, but what we did, we already have bitmaps implemented, we just need to use it in more places. So what we did is we extract this interface, the reachability checker interface. Yes, it will choose based on the repository if you want a pedestrian walk or a bitmap walk. In the pedestrian walk, basically you take the graph, all the visible references, mark them as a starting point, and then you start walking until you find the object that you are looking for. Of course, again, 1.8 million operations saying start here can be a considerable amount of time, only setting up that, and then you need to still walk until the object. So then we did also the bitmapped implementation. What it means is that we are now going to walk. We create a bitmap of the things that we have reached so far, and with each new commit, we check if it is there. And we do that starting with one branch, then another, then another, then another. So first, we try to make this faster doing incremental work. So try first in one branch instead of starting with all of them at the same time. And second, using bitmaps to know either we already have been here, and what we are looking for is not there, or yes, and the navigation, and then we avoid needing to recrawl those nodes. But yeah, we introduced the API, and both implementations, and now it's still, there are some patches open in JGit under review, because we are still trying to fine-tune that. Of course, when we do the branches one by one, it's important to choose carefully what do you check first. And there are cases, if you just take alphabetical order, all the refs changes from Gerrit will go before refs heads. That arguably could be a more interesting branch to look for an object. Then also there is a very expensive, expensive operation that is translating the object IDs into ref commits, so we will try to delay that operation as much as possible. So only when you need to go to the tip of a branch, then do that translation. And limit the depth of bitmap calculation when we are working, hoping to find a bitmap and take a decision on that branch. At the moment, it just does it unbounded, because if the project has bitmaps, eventually you should hit one. But if you don't, that could lead to some problems. And definitely, we're improving also the memory consumption, because the fact that we like bitmaps, it doesn't mean that we like as many bitmaps as you can. So we are trying to use just one or as few as possible, because bitmaps cost a lot of memory. And then we go back to a feature. This is more a work in progress. As far as I know, this is still not yet in the Git client master, and it's called sideband all. Sideband has been in Git since forever. Basically, each line in the protocol can be prefixed with, this is simplifying a lot, can be prefixed with a number, and that says in what channel the message is coming, and is what Git uses to send progress information while preparing the pack file. And as it's designed, it was just to give indication of progress, so it can only send the messages with sideband after the pack file starts. And so look, if this is an important feature that we have even 4 flags to enable, disable, and tune it. These last 2 are what enable sideband all. Enable sideband all is basically answering the protocol, but we still don't advertise the capability. Allow sideband all, that's the advertisement. And sideband all is basically put a sideband indicator, a number on every line, which means that now we can put sideband messages at any point in the communication. And this is important because when we want to implement pack file offloading, we need to introduce a new section in the answer, and for that we need that extra flag before sending the pack file. Because that leads me to pack file offloading. That is the feature that we are working on right now. This is even the spec of pack file offloading is still the best reference. You find it in an email in the Git client mailing list. So let's see, at the moment we have an idea of the protocol and we are doing a first implementation. We're trying there how to fix, how to combine with the authentication and how it works. And the idea is that when you are going to fetch, the server calculates what to send back. And in some cases, for example, in a clone, what the server is going to send back is a pack file as it is. So in that case, instead of streaming those bytes directly, the server could send a URL back to the client. And then the client will complete the operation doing a wget, an HTTP fetch of that URL, which means that it gets all the benefits of using plain HTTP instead of our own socket to pipe the information back. They can also resume downloads if it gets cut in the middle. And this, at the moment, for the client, how it looks is that at the moment of the fetch, it says with what protocols it can fetch pack files. This is a regular, if you don't put this option, you would get a regular fetch of the repository. This is our clone of Eclipse JGit. But in this case, with these options, I hope you can see that it says total 0, delta 0. So in this clone, it's not going to actually send any object, which looks weird. But the repository comes, because what happens on the Wired is that we add this new section, pack file URLs, and it's saying, oh, here you have a hash of the thing that you can, the hash of the file that you can verify the download, and please take your pack file from this URL. So the Git client is actually downloading that, and then says, so I'm ready with everything, and build its indexes and do the client part of it. From the server part, this is you basically upload pack, that is the class that will handle your fetch. Upload to handle the fetch request basically is the class where you are going to say how to translate a pack file into a URL if you want to do that. So upload pack, when it sees that it sends the whole file, will call this class to ask for the mapping. And at the moment, JGit doesn't cover, and it's responsibility of the server implementer to decide that pack file flow. I mean, where to put it to serve it via HTTP, if you want to put it in a CDN, if you want to, and when to refresh and when to recreate those pack files. And then finally, this is a bunch of things that we think that that are going on in JGit. Some already, others in the near future, and others we know that needs to be done even when we don't know when. So we're hoping to use bitmaps more and in more cases, for example, for the connectivity checks on receive pack. So when you push to the server needs to know that everything you are uploading is connected with what the server already has. So if we can do that with bitmaps, that would be a good performance improvement. Then also, the bitmaps are expensive in memory, which means that we don't generate it for every single commit. But we try to be clever to choose where to generate them and try to make it in the most efficient way. Then also, JGit, we support shallow and unshallowing clones. But it is more testing, and we know that there are some bugs, and we are still working on that. We don't have a client implementation of the protocol v2 for JGit, which funnily enough means that we cannot test server options with a JGit written client. But as far as I know, the code is not in a trivial detail, but well, it's something that eventually should happen in JGit. And then there is also floating the idea that we have a lot of deprecated APIs, so at some point we would need to clean that API. And there has been running the idea of maybe creating a next branch that we could do with the clean new API, trying to help with this cleanup. And finally, other things, these are more like design related. There are multiple tries to work around the repository class hierarchy. The people wrap it or subclass or do all kinds of tricks to plug references, reference databases and manipulate it. And there are a couple of patches to do that in different ways. So maybe there is something that requires a bit of design thought in how that class should evolve. Exceptions rework is something that we have been doing on the server side. Eclipse of JGit has its own API compatibility, but in JGit overall, we rely on IO exception to cover absolutely everything, which means, and it's giving us some trouble because we need to know exactly what has failed. So it's a problem, it's a critical problem that the repository is corrupted, don't bother to retry. is that something external has failed, so then maybe a retry would help. So IO exception is not enough information. But again, this requires changing the API and more work on that, so it's not something that can be just done with a commit. And finally, we are also working in submodule subscriptions. This is an early work. I still don't know how it will look on JGit, but we are trying, as we use submodule subscriptions, we want to use it more in a plain world auto, not only on Gerrit, but also for plain Git repositories. So it's something that we are seeing how to move part of that functionality down to the JGit layer. And this was my overview on what is happening on JGit. So now Hangwen will introduce his work on reftables.
Yes. So thank you, Ivan, for the first half of the talk. And now let's get on to the second half, where I'm going to discuss Git as a database. So you know software as a service, where you have one thing and then you make something completely different out of it. And so we do this with Git as well. So Git is a version control system, but we think it's a database, we, the Gerrit team. And so in order to understand, so I first want to explain why we're doing it, and then I'll explain you why this is actually a difficult problem. And then the savior will come, and the savior is called reftable, and I have a small demo as well. And so to start, we first need to think about what is a code review. So a code review is basically code, and then people talking about code. So it's code and metadata. And so the code is easy. We can store that in Git. That's what Git was made for. And then we have metadata. So over here, we have an active review at patch set 20, and then someone says it's great. And then you click the submit button, and it's rebased, and you create a new patch set for the rebase, and the metadata is changed for it to be merged. And so we have patch set 21. And it's great, except in earlier versions of Gerrit, the top half was in Git, and the bottom half was in a SQL database. And things would become difficult if someone at the same time would click the abandon button, because abandon doesn't have a 21st patch set, and the metadata is different. And so if you have two storage systems, if the red half changes one storage system and the green half changes the storage system differently, you'll be in a conflicting situation. So that's not nice. And so it makes it hard to do backups. It makes it you create inconsistencies in the database. And these SQL databases are also hard. Like if you're a user and you decide you want to take your code reviews somewhere else, then how do you get all that data out of the system? And finally, it's just extra complexity because you have a second system to tune. And so we thought we're going to solve that. And there's many reasons why we wanted to solve that, but there's always a reason and an occasion. And so the reason is that these two systems cause problems, but the occasion was that the Megastore team at Google came to us and said, hey, we're going to switch off your storage system in 3 years. You had better make a plan. And so our plan was to never do that again. And so we built this database on top of Git. And so now the metadata is also in Git. And once you do an operation, we change the metadata and the code at the same time in an atomic reference update. And so you think, OK, now the problem is solved. So in order to understand why this is a difficult problem, we first have to look at how Git branches are accessed, and then we'll look at how they're really stored, and we'll see that there's something wrong here. So there's two types of access for Git branches. So first of all, if you know exactly what you're looking for, you say, this is the branch name. give me the data for that branch. So that's random access, basically. There's also something else, which is a prefix search. For example, if I'm looking at all the data pertaining to change 1, 2, 3, I'm looking at all the things whose name is like refs, changes, 1, 2, 3, and then something else. So here you see that as the star. Do you see this? Yeah. And another thing to keep in mind is that we now have a lot of very large repositories that have millions and millions of branches.
Whose fault is that?
It's the fault of the management that staffs these teams with lots of people, so they write lots of code and they submit lots of code. And so it's really a success story. And in general, in the tool space, what we see is that if you build a great system, then everyone says, oh, that's great. You have a system that just works. Let me just abuse it to, let me just use it to put whatever data I need, I put that in your system. I have a database, maybe I can put it into Git. And if you think that's a joke, it's actually something we're struggling with right now. So how does Git store references? And so the most basic form is, so if you look inside how Git stores things, a lot of things, you see on Hacker News or on these sites, people saying, oh, I implemented Git and it took me only 20 lines of Python. And it's because the basic storage structures are really simplistic. And so, for example, if you go to your .git directory, there's a directory called refs, and then there's a subdirectory called heads, and then if you change your master branch, there will be a file there. And the file has 40 characters, it's a hex SHA-1, and that's what the branch is. And so if you want to do random access, you open the file, you read what's inside. That's kind of okay because the file system is actually pretty quick, but it has a large overhead because you have to do system calls, and so they're kind of slow. Now, if you want to do the prefix search, so we want to have everything in a certain directory, then we have to open the directory, and we have to read it, and you have to look at all the entries, and then maybe it's another directory, and then we have to open that directory, and we have to read it, and we have to, et cetera, et cetera. And so that's kind of, that is not great. And also, you take up one file per reference. So if you have 2 million branches, like in the Chromium repository, you'll take 2 million files. And usually files have fixed overhead. So this is not great. And also, if you're on Windows, you're kind of in a difficult position if someone checks in a branch called master with capital letters, because master in capitals is the same as master in small letters. Okay, so this is not great. So what did the folks come up with? They came up with version 2. It's called packed refs. And so instead of having a file per ref, you take all the refs together, you put them you sort them, and then you put them in a file. And so because it's sorted, you can kind of use binary search, and it takes a log n of time to find things. And the prefix search basically looks the same. So if you look for refs changes something, you just look for the first thing that starts with ref changes, and then you just walk through the file. So that's pretty okay. It doesn't take too much storage. Unfortunately, if you now want to change it, you have this file with 2 million refs, and you want to add another one. You have to write another file, copy 2 million refs, then add one at the bottom, or actually one in the middle, and then you put it over the original file. So it's very expensive to write. So this brings us to how it actually works in practice today. So you do both. You have the packed version, and then if you want to make a write, then you make a separate file. And so you get kind of the advantages of both schemes, but it's very difficult to understand what is happening because if you have the packed refs file and a loose file, which one is if they conflict on the data that's in there, which one is going to win, because you use timestamps. But maybe the resolution of the timestamps isn't good enough to decide which one comes first. And another big problem, Martin pointed this out this week to me, is that it doesn't actually have a mechanism to delete things. And so if you want to delete things, you have to copy the whole file, remove a line, and then write it again. And so it's super expensive. And so finally, we came at this discussion because we wanted to have something that is atomic. So we changed multiple things, and either all goes through or it all fails. And because this is all based on the file system, the only way in the file system to do transactions is to do things with single files. So single files you can use atomically. You can create them and it fails or it succeeds. You can rename them and it fails or it succeeds. But if you have two files, there is no way to coordinate. And so in order to do transactions, you have to make one big file of things. Then you can do a change, and then you can have transactions. Basically, you have this file with 2 million lines, and you remove and add lines to the file, and then you copy it and rename it. And so it's, again, very, very expensive. So is there hope? This is a dramatic moment. Everyone is crying. Is there hope? And yes, there is hope. So in order to understand how we can fix this, there's one important observation to make. If we can read things quickly, then we have the problem solved. Because if we read things quickly, we can write small updates in separate files, and then we merge them on reading, we merge them together in memory. So for example, I put an example here. So you start off in this situation, and then someone advances the master branch to the number of the devil, the SHA-1 of the devil. And then a while later, someone deletes the next branch. And so when you're looking at this, you can actually start from the bottom here, reading. And if you're looking for the master branch, you go from the bottom until you encounter master. And then you end up here, and you decide, OK, this is the SHA-1 of the devil. If you're looking for the stable branch, you do the same. You go from the bottom, and then you end up at the first one, and conclude that it's this SHA-1. So if we can read things quickly, then we're done, and we can just have a single file that lists these chunks, these files, and the list of tables will be the thing that provides us transactions. So how can we read things quickly? So one of the problems with this large packed ref text file is that it's a text file. And actually, our devices, they like to work in blocks. They have blocks of 512 bytes or 4 kilobytes, or in the case at Google, 64 kilobytes. So reading a large chunk of data is usually, reading a small chunk of data is just as expensive as reading a large chunk of data. So it makes sense to organize your data around these large chunks. And so how do we do that? Well, we store the keys in sorted order. So we can do binary search, and we can do prefix by jumping to the first entry that we're interested in. And then as an optimization, we do something called prefix compression. So if you looked at the previous, yes. If you look at this diagram over here, you see that a lot of data is actually duplicate. Like the refs changes is repeated over and over. And so this is not very efficient. So we compress that. So instead of repeating ourselves, we just store an integer, a small integer, that tells us how much of the key was the same as the previous one. And so now we have to store a lot less data. But then how can we find our way around? Because if we do that, all the records have different sizes. And so we do that by storing restarts. So whenever we have decide to store the full name, we mark within the block where that is, and then we know if we want to look for something, we first look for the full name that is kind of where we want to be. So let's say we want to find this one, we go here, and then we just walk forward until we find the ref that we need. Okay, so this is how we organize blocks. Then, if we want to store a lot of data, we just write lots of blocks. And if you have a lot of blocks, then how do you find your way around these blocks? Well, you take the last key of each block, and you put that in a different type of block, which is the index block over here. So say you want to look for something over here, then you first look, let's say we're looking for 1, 2, 3, 4, 5, right? It's somewhere over here. Then we look at the first key in this block that is beyond there. That will be the first one. And then we know that we have to go all the way here. And now we're inside a block. And as we saw in the last slide, we already know how to do a block. And so we can do the thing we want to do. And so here you see one index block. But if you have a very large table, you will also have quite a lot of index blocks. So you can also make index blocks of index blocks. And again, see that here the keys have repetitive data, so you can do prefix compression again. Well, if we're inventing a new format for storing the ref database, we might as well fix all the other problems we have with this as well. And one thing is that there is the ref log. So it's a log of how branches change over time. And it used to be stored separately. If we have a new format, we can store this data together with the actual ref data. And it's nice because you can have ref logs for things that are, there's no more conflict between directories and files, because the ref logs used to be files on the file system. And so you cannot have something that is a file containing a ref log and a directory that contains ref logs for the sub-branches. And Martin looks at me a little puzzled. This is a fundamental problem with the ref log storage. It's fixed now in the new storage format, and it's also atomic with the ref data. A second thing which is really nice is that we do inverse lookups all the time. So we get a SHA-1 from somewhere, and we want to know which branch is associated with it. If we have this storage format, we can store that as well. So there's an inverse index where you store which branches correspond to a SHA-1, and it makes it much faster to do visibility checks. And so the graph you see here is the Chromium push performance. And it turns out that Gerrit has a part where you push a change that we try to find out if you've pushed this change before. That is, does a branch exist with the exact same SHA-1? And it used to go over all the branches to find that branch. With the ref table format, we don't need to do that. And surprise, it took 30% out of our push performance. And these are seconds, so this actually went down from 30 to 20 seconds. A significant speed improvement. So I talked about reasons and occasions. The reason, I've explained to you the reason why you want this format, because you're running Gerrit on servers that use local file system. But we at Google used to store this stuff in Bigtable in the following way. So we had row keys. So Android is the host, Wi-Fi is the repository, and then we had the ref name. And this is a pretty reasonable way to store it because the Bigtable is sorted. And so you can do the same thing with binary search and prefix iteration. Except that we don't trust the Bigtable team. We trust that they run storage for us, but the data here is owned by the Android team, and we don't want the storage team to be able to see what we are working on. That's just, in a large company like Google, you have to encrypt things at rest. And then what happens to this beautiful sorted list is that it looks like this. Oh, sorry. It looks like this, and so all the structure is gone, and when you want to look for a prefix search, you don't know how that ends up encrypted, and so you have to read the whole damn thing, the whole 2 million rows to figure out, decrypt them, and then figure out which are the ones you really are interested in. And so this is the reason why Sean in August implemented this. He invented this. He wrote most of the code and then got his team, from Terry's team actually, to roll it out. And this is Terry's favorite graph, where it's the time that it takes to fetch data from our internal deployment. And you can see that there's 2 points where it goes down. So the right point is where we deploy the Git protocol v2 that is now also available in a Gerrit near you in version 3.1, so you should really use it. But the first change is this new ref database format. And if you think this improvement is not impressive, this is a logarithmic chart. So this is like a 5 to 10x improvement in speed. So Sean did this for our deployment at Google. He wrote the code to serialize the format to use it. But the part where it is available to the normal mortals that run it on local storage, no one ever did that until a couple months ago, when I thought, maybe I should fix this. And so this is, I wrote the code, so there's, I can show you it is patch set 86 now. I think Matthias said it's almost there, so hopefully next week it will be submitted. And I just wanted to show you what this looks like. And so this is not a super, so I have here a Gerrit site. So there's a Gerrit site. I make this a little bit larger. Can people read this? Okay, so this is the traditional storage. So you see a file called packed refs. We talked about this this file, and there's a directory called refs, and there's heads, and there's probably, yeah, there's master. And so there's there's 3,500 branches, so there's probably 1,700 changes here. So I have a, wait, where did it go? Okay, I have a small program that creates a change. And so creating a change means that you create the code ref and you create the metadata ref. And so you create 2 refs at the same time, and this is a transaction. And so if I do this on packed refs, you see that it does like 7 changes per second, roughly. So median 140, yeah, that's 7 per second. Now I also have another project called reftable. And so here you see it, and you see a refs, make it a little bit bigger. There's a refs.old. That's a directory where it used to have the old format, but the new refs is actually the list of ref tables. As I said before, you have a list of tables where you store the data, and the actual tables are here. As you can see, they are kind of, every time you write a small one at the bottom, if you have a lot of small ones, then you sort of have to put them compact them together to make a bigger one. And so you see that there's kind of geometrically powers of 2 size. And we can run the same benchmark here. And you see that it does like 15 changes per second, and it's roughly twice as fast. And so this is a repository with only 1,700 changes, so this is quite small. If you make the repository much larger, then the difference will be equivalently larger. You will see that the ref table performance will be roughly constant, whereas the larger repository will slow down. Yeah, that's my demo. Yes. So I also did a small benchmark where you just write this data without a Git repository being involved, and you can see you can do about 1,000 writes per second on local SSD, or you can do 50 per second if you have an NFS server. And the benchmark is roughly what I just showed you. So, what's the status of this? So I showed you the change. It's almost ready. It will be submitted. It will be available in the next Gerrit. Maybe we even backport it to 3.1. Yeah, that would be nice. It is transparent, so JGit doesn't really, the higher level of JGit and Gerrit doesn't know how you store the ref database on disk, so it should just work. And if you're kind of scared, you can actually convert back and forth and try out and see what happens. The bad news is that Git core doesn't support it. So if you run normal command line Git in a ref table and enable the repository, it will be really confused. I did write an implementation of the same code in C. And I'll try to convince the Git upstream project to adopt it, but I do this. So I'm actually the manager for the backend team. So whenever there's something important for us to do, I don't do it. But this because I have to be in meetings and coach my team and so forth. But this is kind of an interesting side project for me. And then there's also a long-term vision or a long-term reason. So we at Google, we design efforts like the checks, the CI integration I talked about earlier, thinking about the storage characteristics of our own system. And then we want to sort of give this to the world. Then some people come and say to me, but you can't run this because it's too slow, because we don't have your fancy infrastructure. And it's actually a problem for us because now we have to think about our own problems, but also the problems of the sort of community version of Gerrit, which has different characteristics. And so if the community version, open source Gerrit, has this library, then our life becomes much easier because we can just assume that things are fast everywhere. Yeah, so I hope that this will go in and be a success. And that's all I have, I think.
Yeah. Questions here. So the questions are for. Let's read the questions. I'm sorry. We are a little bit out of time, but it's fine.
Yes, is my audio working? Yeah. Well, at least the first one seems easy. So can the pack file offloading be used for CDN support for the Git clone? Yes, in principle, that was one of the original ideas in actually using a CDN. As long as it's something reachable via plain HTTP, that should work.
Click mark is answered. Here we get to the next one.
What's the relationship between pack file offloading and Git LFS? Are they solving the same problem? Are they going to work together? I'm not so sure about that one, but LFS is more related with partial clones than really with, that's really with the part. Pack file offloading, if you think that the first use is the Git clone, so getting the whole copy of the repository.
I actually answered this at last year's Git merge, or this year's, earlier this year's Git merge. So.
Yeah, so I actually gave a talk at Git Merge last spring that answered this question. And basically, LFS is kind of an intrusive way to do the same thing. This is pulling what LFS is doing and hiding it behind the scenes of the Git protocol, more or less, or it's integrating it with the Git protocol. And so you have a lot more ability to move from place to place, right? Because what LFS is doing, it's saying, hey, you've got a large object. I'm going to send that up to a specific server and return a URL to that server, and then what I check in to the repository is that URL. So then you're kind of stuck with the URL permanently in your history. This is all done behind the scenes within the Git protocol, so that's kind of the difference between the two.
Hey, I'm getting all of them. Is because of the time?
I don't know. He's the boss.
When is JGit going to support Git protocol v2? Otherwise, the replication plugin won't be able to leverage the Gerrit 3.1 improvements. I guess this is supporting it on the client,
Client side, yeah.
on the client side.
Yeah. Actually, I think if JGit needs to go push.
I think David Ostrowski answered this question earlier in his. I believe David Ostrowski answered this question in his talk. The answer is any motivated person can send a patch and we will be very happy.
Is there any plan to improve Git LFS support in JGit or to abandon it?
So I can piggyback on what Terry was saying before and sort of do a little bad-mouthing of Git LFS. Git LFS was created to solve this problem of handling large files in Git repositories. And it was serving a very serious need, and really nothing else did that. But there's this whole design space of different possible ways to do this that were considered. And the sort of underlying principle in Git LFS is change Git as little as possible. It turns out that just by changing Git a little, you can get lots of benefits. So one of them is that you don't have to sort of bake into your repository this decision of which files you want to have offloaded, like Terry alluded to. So JGit has Git LFS support. There's no reason to remove that. I don't think anyone's going to abandon it unless they're happily using something else.
Actually, Jonathan mentioned another good thing there, which is that the decision of which files go into LFS is baked in. And so if some developer doesn't have the LFS plugin in place and they push up a 2 GB binary, that's in your repository and it's stuck there. So the advantage of what we're trying to do, working with Jonathan's team with the Git upstream project and trying to get in the server side of JGit, is to support that being very dynamic. I want all my objects greater than 1 megabyte to actually be stored in, content, alternate storage system.
Is there any work going on around the implementation of V2 in the client? We talked about that already. Patches are welcome.
Is anyone working in supporting reftable in the main C-based, Git code base, and libgit? So again, I wrote after, so I did the part where, so Sean wrote the serialization for the reftable format, and then I sort of hooked that up with a file repository in JGit. And then I thought, okay, now I know how it kind of works. I think I know how it works, so I should be able to write one from scratch. And so I wrote one in Go. To really understand it, that kind of works. And I have one in C based, a straightforward port of the Go code. And I hope to use that to, I hope to be able to integrate that in both in libgit2 and in the Git code. But I'm the manager and I don't have a lot of time, so with some reservation. Nasser.
piggybacking on your last answer there. So if you run out of time, is it something Google, somebody else will take on as, actual day job?
So, the question is if this is a day job for someone at Google?
Assuming you run out of time to do it.
Yeah.
I think it could easily be a day job for someone at Microsoft. They have a big motivation to overcome. They have so much pain with the non-case sensitive nature of the file systems they sit on, so they would really love to see loose refs, pack refs just gone from Git, right? So they also have day jobs that are keeping them busy on other things, but if it's the kind of case that once you get enough momentum, maybe if we just connect you up with the right people, they can take it, because a lot of getting things into the Git upstream project is doing it the Linux development way of patches over email and all that kind of stuff, which is a very different development experience from using Gerrit. So a manager may not have time to successfully navigate that, but if the bulk of the code is there, then it might be something someone can pick up and push in.
3, 2, 1. Okay.
Thank you.